Today on Green Science Oregon, we're taking a good look at the future of solar energy. A group of students at Oregon State University has formed their very own solar vehicle team. We'll take a look at their latest vehicle and learn how constructing the solar car was a combined group effort. We'll also visit OSU's School of Chemical, Biological, and Environmental Engineering and the OPIC Lab, where laboratory research is being done to develop thin-film solar cells. One method being used prints a solar energy absorbing solution onto any surface. All coming up next on Green Science Oregon.
My name is Hai-Yue, and I am the co-captain and chief engineer of the OSU Solar Car team.
This is a project involving Oregon State University students to design, build, and race solar-powered vehicles. We're working on our second vehicle. We started the team in 2005. It was actually Hai-Yue who had the idea to start the solar vehicle team from a movie he saw when he was 16. And so he practiced all through high school and for the first part of his university career making electric go-karts for practice making solar-powered cars.
Actually, Hai-Yue, we should just put one of the calipers off. It'll be like 10 times quieter.
Where's Eric? When I was in high school, I was a sophomore in high school, my brother found a movie about high school team, or a group of high school students starting a solar car team and taking their solar car on a solar car race. And I was like, hey, that sounds like a lot of fun. I want to go do that. But you know, it was not as easy as I thought in high school, so I kept that in the back burner until I came to college, and when I came to college, I started the OSU Electrothon team, which is a team that built like a electric go-kart that was in preparation for a solar car team. And in 2005, me and Kathy, the other co-captain, we started the OSU Solar Car team, and since then, we produced 2 cars.
This vehicle started out as a design of a body that would fit around a person, and then we had to design a frame to fit inside that for structural integrity. We began by building this titanium frame, which was mostly welded and bent to make this frame. And then we also made the carbon fiber body, but we had to make a mold and a plug for the body, which are really, really large pieces that are kind of shaped like the car to make this carbon fiber body. Those were the major structural components, but then on top of that we had to assemble a battery pack. We had to acquire a motor and motor controller and design a lot of the electronics that controls the vehicle. And we also were donated from Solar World, we were donated 700 bare solar cells to make this solar array, and so we cut, soldered, laminated, and strung together the solar array.
This solar car is a inverted tricycle design, meaning it has 2 wheels in the front and a single tire in the back. We only have 3 wheels to improve the frictional drag of the car. Having 3 wheels creates less friction than 4. We actually have a Star Trek touch interface on our steering wheel. We're one of the only cars that has a LCD touch control interface instead of like a mechanical on-off switch for a lot of its controls. Having an LCD touchscreen interface allows us to have fewer wires in our car, which in turn means higher reliability all the way around. It weighs about 440 pounds. It's got a carbon fiber body and a titanium chassis. We're actually one of the only solar car teams that has a titanium chassis because titanium is usually very expensive, right? But we have our our local sponsors from ATI Pachang, who has given us more than $24,000 of titanium for our car. So our car was able to have the same strength with half the weight for a typical chassis. The power input on a solar car on a bright sunny day is about 2/3 the power of a hairdryer. So a hairdryer is 18,000 or 1,800 watts. Our solar car takes in about 1,000 watts peak. And so with this power, our car is able to go on the highways and attain highway speeds. When this car closes down, you will see that our car is a very small frontal area with a very small coefficient of drag. So it is designed to cut through the air. The actual shape of the car is actually based on an airfoil design. If you look on the side view of the car, it actually is the same profile as like an airplane, actually. You see, we actually had to perform calculations to ensure that our car does not fly when we're driving.
Green Science Oregon is brought to you by Oregon State University, where faculty, students, and research are powered by Orange.
The world around us is full of possibilities. At Oregon State University, we're making them a reality. Ensuring the water you drink is clean, driving innovations to produce healthy foods, and feed a hungry world. Harnessing clean, renewable energy to power your life. Our solutions are making a difference you can see every day. That's what it means to be powered by Orange.
Yeah. E-brake? The e-brake was sitting on the wheel a little bit.
That's okay.
So I think we've just turned our tire into a slick, but...
Oh, stinky.
We can see this settled down.
Oh, did it?
On the tire when we lifted it up.
We have a group of approximately 20 to 25 like core students, and we have students from every field, from electrical engineering, mechanical engineering, to history and geology and everything in between. We take everybody.
The team means a lot to us personally, in that this is just the beginning of a life that we want to have involving alternative transportation and education around alternative transportation.
My name's Danielle, and I helped assemble the solar array. We cut them at OHP using a laser cutter and then soldered them together with bus bars and created the solar panels, which are 12 cells for each one. We soldered 6 half cells in a series and then attached them with a bypass diode and did another 6, so each panel has 12 half cells. And then we have 7 sub-arrays on the car. There's 1,030 half cells on the car, or 515 full cells.
I'm Eric Hyde, and I'm a mechanical engineering senior at Oregon State University, and I work on the solar vehicle. Part of what I do here in the solar car, I started off with a lot of the body mechanics and working on constructing the body, and then I moved on to design and implementation and working with several of the people on a senior project team to upgrade the latch system, lift system, and the wheel fairings on the solar car. We've been doing a lot of finite element analysis in SolidWorks in order to make sure our components work before we actually build them. And we've been having a lot of fun doing it.
My name's David O'Gorman. I was the chief electrical engineer for the OSU solar vehicle team. So for this vehicle, we had to design all the electronics ourselves. I mean, there are things that are commonly available that could kind of do what we needed him to do, but for the skill set we had available for the team and for the amount of funding, it was most efficient and not very difficult overall for us to design all the vehicle electronics ourselves. We made one unit that monitors the charge and discharge of all the batteries in the vehicle for a very large pack of lithium-ion batteries. There were clear rules about how it had to be monitored so that things wouldn't catch fire and be used most efficiently. We had to make all the electronics for controlling the motor ourselves, and then we had to make the electronics for just body housekeeping functions like the turn signals, horn, all that sort of thing. This is actually the body control module board here. It was designed by some of the people on the team. It's a modular design. These are our processor carriers. They carry the smarts for the vehicle. It hooks to an in-vehicle network that communicates between all the circuit boards and the control computer for them. All the different lights and sounds on the vehicle plug in here. All the motor controls plug in here, and the vehicle network plugs in here. After these boards were designed, we sent them out. They came back, and they were actually manufactured here by the students and members of the team. This whole house was converted over to the solar car production facility. Basically, we took over the kitchen table for all the circuit board construction. We had students working in there, putting together the circuit boards, troubleshooting the circuit boards. This area here was used for solar cell assembly. The area over there was solar cell testing, and just piles of material and students working long hours for the last month or two before the trip, get things ready.
Right now what we have is a dedicated group of students, a good solar-powered car, and a lot of potential for outreach and improvement on the solar-powered car. So our current goal is to get as many people involved as possible, to get a lot of publicity, kind of show people what we're doing here, and to bring in a lot more students so that they can have experience with hands-on projects like this. Because there is no other hands-on electric vehicle research at OSU. And so if students want to graduate their program being aware of the intricacies that go into making electric vehicles, they really do need to work on a project like this to get that experience, and that's where a lot of the major car companies are going. Our goal is to continue to improve this vehicle, maybe make some of the less efficient components more efficient, fix up some of the things that we don't like about it, change the designs a little bit, but since we have the major structure, it's not going to be as expensive as an undertaking as making the first version of this car, and just to get more people involved.
Green Science Oregon is brought to you by Oregon State University, where faculty, students, and research are powered by Orange.
I'm Greg Herman. I'm an associate professor in the School of Chemical, Biological, and Environmental Engineering at Oregon State University. I'm also associate director of the OPIC Lab, which is the Oregon Process Innovation Center for Sustainable Solar Cell Manufacturing, which is an Oregon-based signature research facility. The Oregon Process Innovation Center for Sustainable Solar Cell Manufacturing is a signature research facility where we're able to work in the scale-up of nanomaterials synthesis, thin film synthesis for solar cell manufacturing. Essentially, the idea is we're taking research that's been developed at Oregon State University and other locations and able to transfer that onto a larger scale. So instead of making solar cells that are about that large, we're first scaling up to solar cells that are about this large, and then we're going to the point where we're scaling up to solar cells that are about 12 inches wide and can be a large variety of lengths from 10 feet to hundreds of feet. So the main purpose of the lab is to develop processes that were developed at OSU and scale them up to show that they're sustainable manufacturing processes that industry will be interested in and be able to make solar cells in the future with. It's primarily a nanomaterials approach, but we're also working at scales even smaller than nanotechnology. We're working at the molecular scale as well. So we're able to provide deposit films onto substrates where we're actually using microreactors to create reactive intermediates, and these reactive intermediates then form thin films for solar cells. The OPIC lab, we've moved in just in August 2010. We have a variety of equipment that we've brought into the lab for characterization of the materials and characterization of the processes. These include Fourier transformed IR spectroscopy. We have a mass spectrometer so that we can actually measure the processes as we're running solutions through the microreactors. We have atomic force microscopy so that we can actually start looking at the nanoscale materials that we're developing. Behind me we have a continuous flow microreactor for the synthesis of these nanomaterials. And in the bay that's just right outside the lab, we have a solar cell testing capability so that we can actually have be able to characterize our cells, measure the efficiencies. The instrumentation capabilities that are coming include a roll-to-roll coder. So if you consider newspaper printing or magazine printing, these are high volume processes. And we're bringing in a tool capability so that we can actually print solar cells using similar technology, so that we can actually make these cells extremely quickly and extremely cheaply. I think one of the strengths of the lab is that we're actually at a point where we're working with companies that are essentially startups, which are single individuals. We have a few of these are working directly with the researchers in the lab, but we're also working with international companies, that the research labs that are in the Northwest. So we have capabilities that don't only just appeal to people in Oregon, but we also have research that appeals to people, research centers and companies that are in Japan, Germany, Taiwan, and others. So I think we're making a lot of inroads in terms of how we're going to move the technology from this lab into manufacturing and benefit the state of Oregon.
As a lab manager here for the OPIC lab, I'm in charge of keeping track of the students that are working here and making sure that they have the resources that they need. I also interface with the MBI here, which is the space that we're using for the lab. We have a lot of different type of people that use the lab. We have industry people that are well established and maybe trying to get into a new niche in the industry, but we also have people that are very, very small businesses, maybe just doing research practically in their garages or in their living rooms, but they have this lab as an opportunity to grow.
OSU's School of Chemical, Biological, and Environmental Engineering is home to a number of research projects in conjunction with the OPIC lab, including thin-film solar cell and anti-reflective coating development.
And this one is the anti-reflective coating on glass substrate. So when we write, the instant light reached on surface, the transparent surface, there is the 8% of the reflection, and then finally 92% absorption pass through the substrate. So if we eliminate the reflection about 8%, and the 100% of light source can pass through the whole substrate, and then using the 100% of light source to generate the solar energy. So it will be perfect. So if we use the ARC coating, so we can eliminate the light reflection on the surface. So here, so we deposit the silicon nanoparticle, so synthesized by the solution-based deposition in our lab. So, and then deposit on the large area substrate. It's a very simple method. This one is the eyeglass. Eyeglass also has the anti-reflective coating. So if we also deposit the ARC coating on the eyeglass, we can also reduce the reflections. Also, we can get a clear image on the eyeglass.
This is first is a thin film solar cell. The absorber we call it CIGS, copper, indium, gallium diselenide. So it's a unique thin film solar cell materials, and right now, I think the efficiency, the energy conversion efficiency is the highest for thin film solar cell. And but the problem is coming out. We're using the conventional method is vacuum technology. The cost is high and the output is low. So in our lab, we try to using solution-based deposition method to deposit the absorber layer. We call it CIG6. And using our method, we can printing our absorber layer on the substrate. It's a molybdenum substrate. Then we do some post-processing and deposit other layers on top. Then we got similar device as a vacuum technology. So far, we already make the cell in the substrate itself. The efficiency, conversion efficiency is very promising and comparable with other technology.
Coming up next time on Green Science Oregon.
This device you see right here has a sealed chamber that's attached to a hydraulic press. And this allows us to place the wood inside the chamber and close it up and then subject it to pressurized steam prior to applying a compression force to increase the density. And we literally crush the wood, but we crush it without causing fractures in the cell wall structure. At the end of the process, the wood has been cooled down below 100 degrees C, and the density has been increased. Typically, the density increase will be about 3 to perhaps 4 times denser than the initial density of the wood when we put it in there.
What I've got for you is a steam distillation system. And what I'm hoping to do is extract some essential oils out of western juniper, which I've collected from Sisters, Oregon. And what I've done is with those branches, I've taken the foliage off and put it inside of this still. What I'll do is heat that still up, boil some water, and that water vapor will travel through the foliage, and with that heat we'll extract some essential oils. It'll run through the top of the still, follow through a condenser, condense down, and what will come out is a oil-water mix. And what I have then is something that I can remove the water from and have potentially a wood preservative.